We're going to go over sprint number 28. We have 10 roots, R1 through R10, of the polynomial x to the 10th minus x plus 1. Then there exists relatively prime positive integers m and n such that m over n equals 1 over 1 minus r1 to the 10th plus 1 over 1 minus r2 to the 10th all the way to 1 over 1 plus r10 to the 10th. Compute the remainder when n plus n is divided by 1024. All right, so this sum looks kind of scary because we're summing basically reciprocals of 10th powers, which is not very pleasant, but maybe we can use some properties of polynomials in relation to roots. Let's let f of x be x to the 10th minus x plus 1. Okay. We know it has 10 roots, and since it's a monic polynomial, it can be written as x minus r1 times x minus r2 all the way to x minus r10. So basically, when you plug in r1 or r2 or all the way to r10, you'll get 0. So if we plug in some ri between 1 and 10, we'll get ri to the 10 minus ri plus 1, and that's going to be 0. This is particularly useful because we can rewrite this sum here as something else. And we see from this ri to the 10 equals ri minus 1. We see that if we directly substitute 1 minus ri to the r1 to the 10th plus 1 over 1 minus r2 to the 10th all the way to 1 over 1 minus r10 to the 10th. We substitute ri to the 10th for I between 1 and 10 with ri minus 1. We see that this is an equivalent to 1 over 2 minus r1 plus 1 over 2 minus r2 all the way to 1 over 2 minus r to the 10th. And now this becomes very manageable to work with because we converted sums of essentially 10th powers, 1 over 10th powers to 1 over some linear term, which is fairly useful here. What we can do from here is that we see that this is fairly similar to like a problem where we need to find like sum of 1 over r1 plus 1 over r2 plus 1 over r3 all the way to 1 over r10. Except this time there's like a transformational term at the bottom. We see that it's like 2 minus that root. And so what we can do is that we can think of evaluating the sum as shifting a polynomial by 2 minus x. Because when you shift a polynomial by some horizontal or vertical factor, additive, it should be additive, then what happens is that your roots will move in the direction of however you're shifting it. And so here, given our original polynomial, if we shift it by 2 minus x, we should be able to evaluate the sum because all those roots are shifted by what we're transforming it by. And so if we do our substitution as x as 2 minus x, we see that we get 2 minus x to the 10th minus 2 minus x plus 1. This sum is actually equivalent to 2 minus r1 times 2 minus r2 times 2 minus r10. And here the numerators will all just be summation of let's say 2 minus, this will be kind of long. It's like 9 factors on each of the 10 terms. One of them will be 2 minus r2, 2 minus r3, all the way to 2 minus r10, and plus all the way to 2 minus r1, 2 minus r2, all the way to 2 minus r9. And the way we get that, the bottom term is easy because all that is just the original polynomial evaluated at x equals 2. We see that when we evaluate that original polynomial at x equals 2, we get that big product at the bottom. And so that's just 2 to the 10th minus 2 plus 1, that's 2 to the 10th minus 1. And here to find the coefficients on the top term, notice that all our roots are transformed. These are all just transformed roots. And so the sum of in the numerator basically is finding the coefficient of the x to the first term in f of 2 minus x, our transformed polynomial. To find that, we see that if we do our sign changes via this formula, we see that this is x to the 10th sign. This needs to be x to the 9th, 8, 7, 6, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and to the 0th power. And so we need to make sure that we take a negative at the end so we get the correct sum on the numerator here. So this is just negative. The x term in 2 minus x to the 10th power is, we see that we need an x to the minus x to the 1st. We have a 2 to the 9th, binomial theorem. And then we have 10 to choose 9. But then don't forget we have a plus 1 here. And so here, plus x here. And so we see that we get x times 10. The minuses cancel on the first term, but not the second term. 10 times 2 to the 9th minus 1. And so our coefficient is basically 10 is 2 by 5. So that's 5 times 2 to the 10th minus 1. Note that 5 times 2 to the 10th minus 1 over 2 to the 10th minus 1 is both numerator and denominator relatively prime to each other. We can actually easily verify this on top, just as our addendum. Let's say this 2 to the 10th is x. Then we can rewrite 5x minus 1 over x minus 1 as 5 times x minus 1 over x minus 1 plus 4 over x minus 1. We get 5x minus 5, and then we add a plus 4 to make the expression equivalent. We say that this is equivalent to 5 plus 4 over x minus 1. But plugging in 2 to the 10th means that this term is basically 0. It's a little bit more than 0, but it won't be an integer. And so we know that the numerator and denominator, when you put in x equals 2 to the 10th, gives you the fraction can't be simplified. The numerator and denominator are relatively prime. And so we can finish things off. We just take the sum of the numerator and denominator. Mod 1024, note that this is actually 2 to the 10th, which is fairly convenient. These two terms go away. They have a remainder of 0 when you divide by 2 to the 10th. We get -2 mod 1024, but add 1024 back because remainders can't be negative. We get 1022. That's answer choice E. And we're done.
This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.